And he's a machine learning engineer at AI Conics in Freiburg, and he has a master's in computer science specializing in AI. And yeah, who in the audience knows what an activation function is? Hopefully all of you or most of you. All right. So if you don't know what an activation function is, you will probably get to know what it is, because he will give us an introduction to a new kind of activation function for machine learning models called the GoLU. And yeah, explain you the unique properties that make it up. So yeah, please welcome him with an applause. Thank you very much.
Thank you, everyone, for this opportunity, especially Timon and the Swiss Python Summit team, for letting me speak about the Gompertz Linear Unit, short GoLU. So GoLU was my master's thesis that I was working on at the machine learning lab at the University of Freiburg. It was supervised by Dr. Mahmoud Safari and Dr. Steven Adriansen, further under the supervision of Dr. Frank Hutter. So as you can see, Gompertz Linear Unit is a new activation function, is a novel activation function from the self-gated family of activation functions. Like you probably know about the Gaussian error linear units, GELU, which has been very famous in the translation models like the T5 architecture or GPT from OpenAI, and also Swish, which came from Google. But before starting, as usual, I dedicate this piece of work to the people I love the most. And a good thing is that the archive and GitHub exists, so you can always check it out. And I would be super happy to receive feedback from this lovely audience. And yes, it has also been accepted for a poster presentation at NeurIPS 2025, happening in San Diego and Mexico City. So let's begin with Gompertz Linear Units. So while doing the Foundations of Deep Learning lectures by Professor Dr. Frank Hutter and Dr. Abhinav Vallada, I was learning about convolutional neural networks, and in that they spoke about the Hubel and Wiesel experiments that took place in 1959. So as you know, researchers have always been fascinated by cats, be it an Erwin Schrödinger or Hubel and Wiesel. So what they did is they took a cat, they tied it to a chair, dilated the eyeballs, and projected light beams in different shapes, and also moved it in different directions. They also connected electrodes to the primary visual cortex of the cat's brain and recorded the signals from those electrodes. What they found is that in specific light orientations or light tilts or the beam tilts, the cat's brain resulted in only a few set of neurons firing, and most of the neurons were in an inactive state. Now, if you think of this mathematically, then it would look like a right-skewed probability distribution of activations in the neurons. So this was my first motivation. The second motivation was followed by the fact that if you have seen the history of activation functions, then usually ReLU is thresholded at 0, also its variance are thresholded at 0. And besides that, also GELU, which is the Gaussian error linear units, and CELU, which is the sigmoid linear unit, they use zero-symmetric gates for self-gating the input. And when you also take the respective first derivatives of these S-shaped functions here, you see that it looks like a Gaussian PDF or like a more spread Gaussian PDF. So my argument was that, why is everything always thresholded at 0? Can we move it? What happens if we move it? Do we get better performance? And with these two motivations, I ran on a journey for 1.5 years to build Gompertz Linear Units, where we did like bunch and lots of experiments across various tasks. You will get to see that later in the slides. Okay, so Gompertz Linear Unit is defined as x times Gompertz x. So as you can see, as I mentioned, it's a self-gated activation function. And further, Gompertz of x is defined as alpha times e to the power minus beta times e to the power minus gamma x, where alpha controls the upper asymptote or the scale of the gate, beta controls the left-right movement, and gamma controls the slope of this linear part here. And yeah, this is the gradient of it. Just so there, it's simple. So the Gompertz function comes from Benjamin Gompertz. It was introduced back in 1825, so a bit of history. It was first used by health insurance companies to calculate human mortality rate. So that is where this Gompertz function comes from. It comes from Benjamin Gompertz, who was a mathematician and also a fellow of the Royal Society in London. Speaking of the probabilistic interpretation, as I mentioned about the right-skewed probability distribution, we also consider the Gumbel distribution as our prior. And we take the Gompertz function, which is actually a cumulative distribution function of the standard Gumbel probability distribution. So that was our prior. So if you see all the respective probability distributions here, which are also the first derivatives of the respective S-shaped gate, you will see that the Gumbel distribution and also this other distribution in a purple color, these two are the only asymmetric functions. Rather, the other two, like the Gaussian and the first derivative of the sigmoid function, are symmetric at 0. The only difference is that Gaussian is more peaked, while the first derivative of sigmoid function looks more Latykurtic. And as you can see, our prior assumes that GoLU does a sparse feature prediction because most of the density is spread at 0, while we focus very less on, or we retain very, very few strong positive features. Moving on to the next set of properties, the first property that GoLU introduces is variance reduction. So to prove this, what we do is we do a very simple experiment. We take the very famous Sephartan dataset and randomly sample 4 images, as you can see on the right-hand side of the slide. So we have a frog, airplane, deer, and automobile. We pass these images through a 3x3 2D convolution followed by batch normalization, and then we apply different activation functions and observe what the variance of the latent representation is. And to our surprise, we find that for all the 4 images, the variance of the latent representation with GoLU is less. So this directly implies that GoLU helps us cut through noise in the latent representation and retain only the strongest features that are necessary for making a prediction. And as you all know, that ReLU came from the godfather of AI, which is Geoffrey Hinton. And he proposed that we always clip out the negative space and only retain the positive space. He was true. We also observed something similar, except the fact that ReLU was not smooth and it was discontinuous at 0, while GoLU gives you a much more smoother landscape here, also with activation profile which is closer to 0 on both the negative and the positive regions of the feature. Now, you might wonder, why do we reduce, or how do we reduce variance? So this can be visualized when you plot the respective S-shaped gate. So in all these plots, you will usually observe that the gate for GoLU, which is the Gompertz function, is always usually slightly towards the right-hand side, which naturally follows from the standard Gumbel distribution. So we don't do anything. We don't shift the probability distribution. We don't shift the gate. It exists naturally as is. And every time, for every input, what we observe is that it assigns a relatively smaller value to self-gate the input, and this is what helps us cut through the noise and retain important features in the latent representation. The next property that we observe with GoLU is the squeezing effect. So we do the same experiment. We take a 3x3 2D convolution followed by batch normalization, and then we pass this image through different activation functions, and we see that with GoLU, what you can do is that you can represent the same set of features in a more compact region, which helps the model get less complicated. On the contrary, if you see the distribution of the activations from the other activation functions, you will see that they are more spread, which basically stretches your vectors and matrices in the latent representation. So that is not what we want. We want very simple networks that can do standard predictions. This assumption of having a right-skewed probability distribution was also proved when we saw our ResNet 50 that we trained on the ImageNet dataset. So when we took the last activation map right before the global average pooling, which is usually followed by a fully connected classification head, we saw that when compared to other activation functions like GELU, Swish, and MISH, GoLU always provided a more dense activation distribution towards 0 while retaining at the same time the strong features for doing the predictions. The third property that we see with GoLU is also very interesting. So we do another experiment to prove that GoLU makes your training very stable. So what we do is we take ResNet 20, we train it on Cephar 10, and after training the model on the respective activation functions, we do some noise addition or perturbation to the learned weights, and we observe that GoLU always provides a much smoother loss landscape. So what we do is that we sample 2 different directions of the same shape as the trained weights, and in a grid of alpha and beta linearly separated, we run inference through the test set of the Cephar 10 dataset, and we just get the loss from the perturbed weights. And this directly implies that the weights when trained with GoLU, or the networks that are trained with GoLU, are more robust to perturbations. This is because we achieve a more flatter region of the loss landscape. So because we are in a more flatter region of the loss landscape, even changing the weights does not affect the performance of the model. And we all know that from our linear algebra lessons that usually a model which is well conditioned is preferred, which means that the Hessian of the loss function with respect to the weights should always be better. So yeah, that simply implies that GoLU as an activation function induces more stable training in the network in comparison to the other activation function. And by the way, if you do not know, then GELU was the most favored activation function in the last 1 decade. It was really hard to defeat this activation function, and yeah, after a decade, we using asymmetry in our function, we defeat GELU or surpass GELU. Plotting the distribution of the losses that we see in the previous slide, we always observe that GoLU provides the smallest average loss because it's more shifted on the left-hand side, and also it provides a smaller variance in the loss landscape, which means that the model doesn't change so much once it reaches a stable region, and therefore we can always say that the expected performance with GoLU is supposed to be much, much, much better. The third most interesting property, and this is actually really interesting for the entire machine learning community that we find, is that because of the variance reduction property, that with smaller self-gating values, we receive smaller gradients and also relatively slightly smaller parameter updates, which is also similar to dropout. We often see that the learned weights from GoLU are more spread in comparison to the other activation functions. And this also helps us in capturing better features from latent representation. And this further opens a new research question in the community, because in the past, we all had a notion that L1, L2 regularization helped us receive generalization or create a state of generalization in the model. But then L1, L2 regularization always induced sparsity in the weights. So this opens a new dimension in the space of the machine learning community. To further improve the performance of the activation function and also do an apples-to-apples comparison, because I use PyTorch as a framework for doing all the trainings and benchmarking the activation function, I had to build a CUDA kernel. So I jumped into the GitHub repository of PyTorch. It's pretty big. And I was also at times I was lost in the GitHub repository while finding for how PyTorch developed their CUDA kernels. So I referred their template and built my own CUDA kernel for GoLU. And based on that apples-to-apples comparison, we could achieve the same speed as other activation functions in PyTorch. Yes, so GoLU is super simple to use. What you can do is that you can always hit this GitHub link. I will make the slides public for everybody, and then everybody can use this and hit to this link and simply create an activation object and do a forward pass. Just assign a random tensor, do a forward pass, and also do a backward pass that gives you the gradients associated to the input tensor. So with this, I think I come to an end to the properties of GoLU, and now I will talk more about the experiments I did, which is extensive. Okay, so we start with image classification. So in image classification, we leverage the existing Torch Vision, TIM, and CREAM repositories and pipelines for training ResNets, wide ResNet, DenseNet, efficient net from the AutoML team or the neural architecture search team of Google, and then also VITs, Vision Transformers, Tiny, B32, and B16. For language modeling, I refer to Andrej Karpathy's NanoGPT. So if you know, NanoChat has been very famous in the last few days on Hugging Face. That also comes from Andrej Karpathy. And I also leverage the Fair Sequence GitHub repository for training tiny stories on BabyGPT, Open Web Text on GPT-2 Small, and WMT14 on the vanilla transformer. So I trained a vanilla transformer on this task for English to German translation. Further, I also introduced more variety in my tasks and at semantic segmentation, object detection, and instance segmentation, where I trained DeepLab v3, Faster RCNN, RetinaNet, and Mask RCNN on the MS Coco dataset. Also, again, leveraging the Torch Vision training pipelines with the ResNet 50 backbone. And then I also trained a denoising diffusion probabilistic model using the Kimras GitHub repository on the syllabi dataset. So this is not a very big dataset, it's a small dataset just to do a standard proof of concept. And finally, I did lots of learning rate ablations, which consumed too much of GPU hours on some of the best clusters in Germany, while also I did learning ablation studies on the alpha, beta, and gamma parameters of the Gompertz function. But I will not discuss this here because that's not important at this point in time. So going to image classification, you will see that based on all these architectures that we have trained, in most of the cases, we found that GoLU is the best performing activation function. So this is the numbers that you see with the standard errors are basically the top one accuracy from our training benchmarking. And the red colored cells are the ones that perform best, as we see GoLU, and the one in pink are the second best. We also visualize the loss and the top one accuracy on the test set of the ImageNet dataset to see what's exactly happening. And we saw that consistently on a dataset which the model has never seen, GoLU always outperforms the other activation functions like GELU and ReLU, and not only for ResNet 50, but also for VIT. So it's a very generic purpose activation function that you can just plug and play with in any possible architecture. Going with language modeling, again, we see similar performance results that GoLU beats the other activation functions, while GELU being the second best, as I also mentioned in the past. So these small arrows you see in here are indicators if the metric is to be minimized or the metric is to be maximized. So perplexity usually tells us about how the loss looked like or what the next best, what was the probability with which the next best token was chosen. So this tells us that. So we usually minimize the loss. So that's why we also minimize the perplexity, and token accuracy is something that is to be maximized. Similarly, here also we see results that correspond to what we saw in ImageNet. So what's more interesting here is that, as you can see, for example, for GPT-2, you already reach a better performance than GELU or Swish already with lesser number of training iterations. So what you can also do is that if you want the performance to be same as GELU, for example, when compared to GoLU, then you can always train for lesser number of training iterations, and you can reach the same level of accuracy. So this also helps you save time and compute in terms of training. Semantic segmentation was a bit different because the default learning rate did not perform to be the best. So PyTorch, the pipeline from PyTorch and Torch Vision has a default learning rate of 0.02, where ReLU turned out to be the best. But then when we spend some more time doing learning rate ablations, as you see, so the column which is colored in a black border is the default learning rate, and the one in green represents the best learning rate. So we found that not only GoLU, but with a learning rate of 0.01, all other activation functions give a better performance, and then GoLU surpasses all the other activation functions here as well. For object detection, we didn't have to do any learning rate ablations because for faster RCNN and RetinaNet, it was directly very clear that GoLU was the best, and again, the same performance was maintained or consistent across the previous tasks as well. The next was instance segmentation, where we again trained a mask RCNN on MS COCO, and we observed the test box map and the mask map, and we had to do a learning rate ablation here again because the default pipeline from PyTorch or Torch Vision did not help here. And with the learning rate ablation that we did, we found similar results as the semantic segmentation, that going to a relatively higher learning rate of 0.03 gave us a better performance. Finally, we trained models on denoising diffusion probabilistic model. So we trained a denoising diffusion probabilistic model on the syllabay dataset, and we observed the loss, and again, doing a learning rate ablation showed us that GoLU was better and consistent in the performance. After doing all of these experiments, we thought that what happens, and this was basically the last experiment we did, so we thought that what happens if we also flip the distribution of the mesh activation function, so the underlying prior. Because if you take the first derivative of the gate of the mesh activation function, and then you get the probability distribution, that's also asymmetric in nature, except for the fact that it's slightly shifted on the left-hand side, and it's a bit more spread, which retains more variance in the latent representation. So what we did is we simply took the distribution. So here in this plot, you can see this black line, or the black plot, which shows the probability distribution of the underlying mesh activation function. So we did a simple experiment where we flipped this activation function. So we just took f of minus x, and then you can easily flip the function. And then we integrated it further to get the cumulative distribution function. Here on the right-hand side, you can see this plot. And we created a new activation function, which is also similar to GoLU. And we found that even after creating this, GoLU was still the best activation function when compared to this new activation function from flipped mesh that we created. So all in all, what we conclude from these experiments is that no matter what the architecture, no matter what the data set, you can always plug in GoLU, and you can expect to get a better performance on top of any other activation function. And yes, a bit of history of activation functions. So you can see that we introduced GoLU here in 2025, which is a new cell-gated activation function and should belong to the family here. What's also interesting is that if you go to PyTorch, and if you see the list of activation functions there, you will find that multi-head attention exists in the list of activation functions. And that was very surprising to me. And maybe I will leave that as a homework for the audience to know why. Or maybe if you want to know, then we can continue this as a follow-up discussion in the Q&A round. With that, I think I would like to acknowledge Frank and Professor Frank Hutter and Professor Thomas Brooks for examining my thesis back in February this year. And Mahmood for supervising this, and also special thanks to many other people with whom I had lots of over the coffee discussions. And best ideas come when you are having coffee and walking around the campus. So thanks to all these people. I would also finally like to acknowledge the compute time which was provided by all these clusters. So some of the best clusters that I got to use during my master thesis, and we used roughly 200K GPU hours of 200 NVIDIA A100s in almost, 5-6 months probably. With that, I think, I come to an end. Thank you, everybody.
All right. Oh, we already have a question over there.
Please.
Very nice.
Thank you. Okay. Thanks for the talk, but maybe first, if you don't mind, I would say what I didn't like about your talk, because I think that you should have spent much more time on slides that was dedicated to your mom and dad. I think they would be unhappy. You very quickly passed it, so I mean that just for future. Okay, good. But if talking seriously, so I mean that really great ideas, and could you elaborate why maybe you didn't use it on audio data? Because, to the best of my knowledge, GELU is supposed to be like the state of top activation functions on this. And maybe there you could have made a little bit more advantage. You could have maybe shown on audio data, how the activation can work. And also I just checked that you have this issue on GitHub saying that please add GoLU to PyTorch, So I think it was you on 10th of July. Correct me if I'm wrong. So what's going on? Why they do not accept it? Did you tell them about your NeurIPS poster exception? Maybe it would make them faster.
Exactly. That's a really good suggestion by you. I really thank you for the suggestion. After the NeurIPS acceptance, we haven't so far reached out to PyTorch by notifying them. So this has been in talks with my supervisor and also with Frank, my professor. So we are going to reach out to PyTorch and let them know about this. Also, another point, I'm very open to collaborations with the audience. So we have currently the CUDA kernel available, but we are yet to build the kernels for CPU, for Intel GPUs, for Apple M1, M4 chips, and all of that. So if you are really interested, please hit me up on LinkedIn. We'll be very open to collaborate on this extension of the project. Thank you so much. Any other questions?
Is there another question there, right? Or this wasn't the right hand? Okay. Over there.
Yeah, thank you for the great talk. It's very exciting to also see a NeurIPS poster here. I was wondering a bit about these numerical experiments where you showed variance, etc., because as you mentioned, GoLU takes, I think it was 3 parameters, alpha, beta, and gamma. And
by the way, we always set the alpha, beta, and gamma parameters to 1. That corresponds to the standard Gumbel distribution.
Right. Because what I was wondering, especially in this variance example, is what is sort of the baseline variance of each of these activation functions? Because depending on how you choose the parameters, right, you could get a variation. How would it be on a uniform distribution? How would it be on a Gaussian? Did you check that?
I mean, the variance that we record is basically for individual images. So if you see these images that we randomly sampled from the Cepharton dataset, we did this experiment where we passed them through to the convolution, batch norm, and then activations. So so these are for individual images, and there could not probably be a baseline. What do you mean by a baseline? Sorry? Yeah, exactly. So if you have parameters, yes, I have also done these ablation studies for different parameters, alpha, beta, and gamma, and that doesn't give us such good results. So we stick to the default of 1, 1, and 1, which I think is also a good default for the community. So it reduces complexities. So you know that directly using GoLU with the standard parameter values will yield you better performance. So you don't need to do hyperparameter optimization for these 3 hyperparameters. Yeah. Any other questions?
All right. Are there more questions from the audience? Oh, over there, yep.
This may be a very layman question, but it's amazing what you're showing, but you always show only one activation function for the whole network. My question is there any ways that you could have, I mean, you have millions of neurons in there, that you have a mixture of activation functions? Just from the theory, maybe it's totally not from theory with the backtrack and all the differentiation you have to do and the optimizing the loss function. But you have millions of data, you have weights, you optimize, but you always use the same activation function. Is that a must?
Okay, I probably have a follow-up question to understand your question better. So what do you mean by one activation function? Because when we are benchmarking the activations across different architectures and data sets, we have the standard activation functions, which are the most prevalent ones in the community. So
I understand. That's why I'm saying it's maybe a very layman question, but you have millions of neurons, right?
Yes.
In those layers, in the hidden layers. And each of these neurons has the same activation function.
Exactly.
Your GoLU. Now I'm asking why.
You're asking why? That's actually a new research question that we have. We need to do research on that. So there actually, if you see the literature, there have also been other activation functions like splash and so spline functions and so on, or I'm not sure if you also know about CANs, which was a very famous paper last year, Kolmogorov-Arnold networks. So they try to introduce a new activation for every possible neuron, but these papers are theoretically nice. When it comes to empirical evidence, they fail to show results. So it makes complete sense to go with the standard activation functions. Does that answer your question? Partially? I'm sorry. Right. We can do that. We can do that. Do you also know about GLU, gated linear units? So gated linear units was something between LSTMs and multi-head attention, okay? Where they did one linear, so they had one tensor, or one input tensor, they passed it through one linear, and then they had another linear through which they passed it, and further passed that, the second tensor, through an activation and multiplied it with the first linear tensor. So there are also parameterized activation functions that are in use. But again, it's not, not that once. So debugging also becomes difficult, right? When you have too many changes or dynamically changing activation functions in the same neural network, then debugging also becomes difficult. So when you have something which is constant, simple, that already performs well, then you probably might not need. Yeah.
I think you can continue this discussion in the,
exactly.
in the break. So thank you a lot for your time and your talk and flexibility.
Thank you so much for the opportunity.